Good. Yeah, so I'm going to talk about a paper. So I suppose the ostensible topic of my talk is a paper that came out, I guess, in the last month or two with Nathan Benjamin at Princeton and Scott Collier at Harvard. Although what I'm going to be doing for a lot of my talk is kind of stepping back a little bit and trying to talk in a bit more generality. So I'll include a lot of review and a fair amount of history just to put everything in context. And also, I appreciate that a lot of the people here are coming at things from very different backgrounds. You know, some people might have a more math background, a more physics background. I'm happy to adjust on the fly the style of my talk. So for example, you know, the way I have things prepared now, I'll assume, you know, some knowledge of conformal field theory and some basic facts about conformal field theory. But if anything is unclear, or if I'm assuming something that people don't know, then feel free to pipe up and let me know, and I can always adjust on the fly. That's something I'm very happy to do. Okay, so let me just begin by setting the stage. So our basic goal is to quantize general relativity. And the quantization of general relativity is a very difficult thing. And so I'm going to make my life easier. I'm going to try and quantize general relativity in 3 space-time dimensions. So 3 space and 1 time. And when I talk about general relativity, I really mean general relativity. So the action is the usual Einstein-Hilbert action, but I'm going to include a negative cosmological constant, which is the second term in the Einstein-Hilbert action that I have written down here. And I've written it in terms of a parameter L that has dimensions of length. And that is going to set the typical length scale of a solution of this theory. So this is general relativity in 3 dimensions with a negative cosmological constant. The prototypical solutions to this is anti-de Sitter space.
Are you in Euclidean signature?
So when I talk about quantizing gravity, I really mean Lorentzian signature. So 2 space and 1 time dimension. But many of the computations that we do in order to study this theory involve an analytic continuation from Lorentzian time to Euclidean time. So some of the calculations I'll describe later on are Euclidean calculations, but the theory that I'm quantizing is a genuine Lorentzian theory. Good. Thanks for the question. Any other questions? Great. So we're studying general relativity with a negative cosmological constant. And the prototypical solution of that theory is anti-de Sitter space, 3-dimensional anti-de Sitter space. And when I talk about my theory of gravity, I need to specify not just an action, but also a set of boundary conditions. So some prescription for how the metric behaves at infinity. And the prescription that I'm going to choose is that the geometry looks like anti-de Sitter space at infinity, but it is allowed to fluctuate in the interior. So I won't tell you exactly precisely how I define this asymptotically ADS boundary condition. It has to do with exactly how I prescribe the fall off in the metric at large distances. But basically it means that I'm studying the theory with asymptotically ADS boundary conditions. And one very famous fact about this theory, which I can review if you haven't seen it before, is that the set of asymptotic symmetries of this space-time, that is to say, the set of canonical transformations that you can do on the space of geometries with this set of boundary conditions, is actually an infinite dimensional set, an infinite dimensional group of asymptotic symmetries, which is the Virasoro group. So the asymptotic symmetry group and here I should really emphasize it's the asymptotic symmetry group, is given by the Virasoro algebra with a central charge which is determined by this cosmological constant, or the radius L, along with Newton's constant. Again, you could have sort of anticipated that result. The central charge is dimensionless. There are only two dimensionful parameters in the theory, Newton's constant and the curvature radius. So C better be some function of their ratio. And because of that, we expect that this theory of gravity should be equivalent to, or in the language of ADS-CFT, we would say dual to, a conformal field theory. So some sort of local field theory with conformal symmetry in 2 dimensions. And the central charge, which is the parameter C appearing in the Virasoro algebra, that characterizes the anomalous behavior of the theory under conformal transformations, is then going to be matched to the central charge of this corresponding dual conformal field theory. Now, I should emphasize that although I'm using the language of conformal field theory when I write down some of these equations, a lot of the actual calculations I'm going to be doing are really gravity calculations. So calculations in general relativity or quantum general relativity. So our general expectation is that this 3-dimensional gravity theory should be equivalent to a 2-dimensional conformal field theory. And it should be characterized by this central charge that I've called C here. So then we can ask, what does the theory look like in more detail? And the first thing that you'd like to understand is what the spectrum of the theory is. So what do I mean when I say what the spectrum of the theory is? Well, I mean, what are the states of the theory? And when I organize these states, I want to organize them into eigenstates of the Hamiltonian that generates time translations and the rotation operator that generates rotations in 1 dimensions, which is to say, I want to label the states by their energy and spin. So the first thing that you could ask is, what does the spectrum of the theory look like classically? So the spectrum of the theory, that is to say, the set of solutions of general relativity in 2+1 dimensions, is actually rather easy to determine classically. I notice this is one of the real simplifications of working with 2+1 dimensional general relativity instead of 3+1 dimensional general relativity. If I asked you to write down the set of all solutions of 3+1 general relativity, that's a very hard task. But if I ask you to write down the solutions of 2+1 general relativity, that actually turns out to be a rather easy task, at least with the boundary conditions that I've specified. In particular, it turns out that all solutions of 3-dimensional gravity with these boundary conditions are either given by ADS or by a quotient of ADS by some discrete subgroup of the ADS isometry group. So let me just tell you then in one picture what the spectrum of the theory looks like. So we'll characterize the states in the theory by labeling them by their energy and their angular momentum. Okay? So if you want a picture for what anti-de Sitter space looks like, anti-de Sitter space you should think of as looking like a solid cylinder. So the boundary of this cylinder is the asymptotic boundary of anti-de Sitter space. There is a time translation symmetry, and there is a rotation symmetry. And when I characterize the states, I will characterize them by their energy, which is the eigenvalue under time translation, and their angular momentum, which is the eigenvalue under rotation. So one of the states in the theory is empty anti-de Sitter space. That has no energy or angular momentum, so it's given by some state that sits just at the origin in this EJ plane. There are also black hole states. So these are the geometries that were first discovered in the early 90s by Bagnados, Teitelbaum, and Zanelli, known as the BTZ black holes. And
Alex, is
yes,
that a good time to take a question? John is raising.
Absolutely. Question.
John, go ahead.
Question. When you say that the anti-de Sitter is a solution, well, doesn't it depend on the L value? Is it for any L value?
For any positive L.
So
The radius
satisfies this for arbitrary L. Where does the L enter the anti-de Sitter?
L is the curvature radius of anti-de Sitter space.
I see.
Right. Excellent. Good question. So the prototypical solution of general relativity with a positive cosmological constant is de Sitter space. And there, the cosmological constant determines the curvature radius or the Hubble parameter of the de Sitter space. Anti-de Sitter space is the prototypical maximally symmetric solution with negative cosmological constant. And in this case, the parameter L, I chose to write my cosmological constant as 2 over L squared, where L has dimensions of length. So then you would just be able to identify L as the curvature radius or the length scale associated to anti-de Sitter space. Great. Thank you. Please let me know if there are any other questions.
Nico has also a question.
Great.
Nico, go ahead. Oh, I think it's not, no, it's a thumbs up, sorry.
Okay, thumbs up, thank you. Okay, good. Okay, great. So what does the spectrum of the theory look like? So we have empty ADS, which is what we think of as the ground state of the theory. And all of the other states of the theory have positive energy. And the first things that I can tell you about are the black hole solutions of the theory, which all live in this triangular region that I have drawn here. So there are a couple things to note about these black hole solutions. So first of all, in flat space, there are black hole solutions which have arbitrarily small mass. Okay? That means that the gap in the spectrum between flat space and the mass of the lightest black hole is infinitesimally small. It's basically 0. In anti-de Sitter space, however, there is at least a gap between the mass, that is to say the energy of empty space, and the energy of the smallest black hole. Okay? That's why, and this gap is set by the parameter C, which is the only dimensionless parameter that controls the theory. Okay? So in particular, if I write down a dimensionless version of the energy here, then the gap here is of order C, and in fact, it's given by C over 12. The other thing to note is that although you might think that I have drawn the set of black holes in this region up here as a shaded region, those vertical lines do not indicate the fact that this region is shaded. Those vertical lines indicate the quantization of angular momentum. Okay, right? So for example, this middle line here is the set of black holes with angular momentum 0. These are the ones with angular momentum 1, angular momentum 2, angular momentum 3, and so forth. And they all live in this upper triangular region. And the boundary of this region, what is that boundary? That's the place where the area of the event horizon of the black hole shrinks to 0 size. So that boundary is what in the general relativity world you would call the cosmic censorship region. Okay. Good. So these, you might think, are the only, these are the only solutions of the theory. And you would be almost correct for the following reason. In general relativity in 3+1 dimensions, we have lots of different solutions. And these solutions include things like gravitons, gravity waves, perturbative excitations around empty space. But in 2+1 dimensional general relativity, this is a theory that quite famously has no local degrees of freedom. Every solution of 2+1 gravity is a quotient of anti-de Sitter space. So you might think because of that, there are no gravitons in the theory. But that turns out not quite to be the case. And the reason is that we're studying ADS gravity in an asymptotically anti-de Sitter space. And so it turns out that there are excitations of the theory, graviton excitations of the theory, that are not local gravitons, but that are associated with the presence of a boundary. For those of you who've studied Chern-Simons theory or quantum Hall physics, this is actually a fairly familiar effect, right? If you take a Chern-Simons theory, that's a theory that has no local degrees of freedom, right? The solutions, the equations of motion just say that the connection is flat. But if you put it in the presence of a boundary, say you have a quantum Hall system that has some boundary, then they're going to be edge modes that essentially are related to the large gauge transformations that act on the boundary of the theory. And it turns out that exactly the same thing happens in this gravitational theory, except in this case, okay, there's a question that I'm going to get back to. In this case, the analog of the gauge transformations acting on the boundary are diffeomorphisms acting on the boundary. So the point is that when I say that ADS gravity has asymptotically ADS boundary conditions, I'm also specifying a prescription for which diffeomorphisms in the theory should be regarded as pure gauge, and which diffeomorphisms can actually be regarded as creating new states in the theory. And the new states that you create are what people call boundary gravitons. And there is a discrete spectrum of them. So they all are given in the CFT language by Virasoro generators acting on the vacuum, or in the gravitational language, they're given by the action of diffeomorphisms that don't vanish at the boundary of the space-time acting on empty ADS. So there's a few questions in the chat window, which I'll answer in a second. But first, let me just rephrase this all in a slightly different language. So these states that I've referred to in the gravity literature, they're known as boundary gravitons. But in the CFT literature, we would call them Virasoro descendants of the vacuum state, that is to say, of empty anti-de Sitter space. Good. So first, there's a question from Luc Vinet. Could you put a Chern-Simons mass term here? Absolutely. We could have a whole separate discussion about that, but there's a modified version of the theory that you could consider, where you add in a gravitational Chern-Simons term. When you do that, you break parity. So general relativity is a parity invariant theory. Chern-Simons terms are parity odd. So you can break parity by putting in a gravitational Chern-Simons term. When you do that, you now have two copies of the Virasoro algebra, but with different values of the left-moving and right-moving central charge. There are various subtleties that have led to some arguments in the literature as to how one thinks about the gravitational dual of these theories, or the CFT dual of these theories with a gravitational Chern-Simons term. I will just mention one very interesting thing, which is that there is a critical value of the Chern-Simons coupling where you have a left moving central charge and a right moving central charge, but where one of them is set equal to 0. So for that value of the gravitational Chern-Simons coupling, you would expect a theory that's purely holomorphic, okay, that has only left moving degrees of freedom, say. And it turns out that in the study of conformal field theory, holomorphic CFTs or chiral CFTs are much easier to study. In a sense, they're exactly solvable rational conformal field theories. And so that led to a great deal of excitement that one could quantize the theory with this particular value of the gravitational Chern-Simons term. There are some things that work extraordinarily well in that picture and other things that don't. I might not, unless people are super interested, I might not go into that in too much detail. Good, so Robert asks, should the size of the gap be inversely proportional to L? No, it turns out that the size of the gap is proportional to L. Remember here that when I write down the energy and angular momentum, I'm writing this energy computed in units of L. So it's a dimensionless energy. So you have to, so one can put all the factors of L back in here. If you want to come up with a sort of intuitive picture for how to think about gravity in anti-de Sitter space, you should really think of gravity in anti-de Sitter space as being like gravity in a box. And it's a box of size L. And what happens, okay, I'll get back to Manu's question in a second. What happens if you put gravity in a box of size L? Well, at very low energy, you're going to have a bunch of perturbative degrees of freedom, which in this theory of gravity are just the boundary gravitons. But at very high energy, you're going to have black hole states. That's intuitive. If you put a lot of energy in a region of finite size, eventually it'll collapse into a black hole. And if you go through and just do the sort of straightforward dimensional analysis, you'll see that the typical energy is going to be of order L, L over G when that happens, where G is Newton's constant. Good. So Manu says, aren't you putting some singular matter in the theory and what is its dynamics? I'm going to get back to that. In some sense, the entire point of my talk is to determine whether it's necessary to add any additional matter to the theory. Right now, what I'm doing is I'm literally just writing down for you the spectrum of general relativity with no additional assumptions. And then later on, what we're going to argue is that for reasons of unitarity, it's going to be necessary to put in additional degrees of freedom. And if we have time, I'll tell you what those additional degrees of freedom are. Okay. There was another question, are these boundary conditions Brown-Hanot boundary conditions? Yes. When I say asymptotically ADS boundary conditions, that is what I mean. And in fact, I should have, of course, put a citation here to the people who first wrote down this formula, who were Brown and Hanot. Good. Okay. So our goal then is twofold. So first, what we want to do is understand whether there actually is a conformal field theory, a two-dimensional conformal field theory that satisfies all of the axioms of a conformal field theory, namely it's unitary, satisfies all of the symmetry properties of conformal field theory that matches the spectrum. Okay. So the first question, is there a conformal field theory that matches the spectrum? So I'm going to answer this question. I won't be able to give a proof that my answer is correct, but I will describe some evidence for this answer, which is that the answer is no. Okay. But I'll say that I'll describe how there is a very small modification to this proposal that works. Okay? So we could then ask a follow-up question, which is there a theory that almost matches the spectrum? And my answer will be yes. Oh, okay. I should say, maybe I shouldn't say yes. I will say maybe. And I will say, I will make a proposal for what the minimal matter content is that one needs to add in order to have something that looks as close to possible as a quantum theory of general relativity in asymptotically ADS boundary conditions. Good. So maybe this is a good time for me to pause and see if there are any further questions. I apologize, there seems to be a garbage truck idling right outside my window. I'm not sure if you can hear it or not. Good, okay. Any questions? Great.
Sorry, Alex. So when you say there is no CFT that matches this spectrum, could you be more precise about it? Is about you cannot.
Yeah, that's exactly what I'm going to show.
Okay.
Okay. What? Yes. So what I'm going to do is so the proof relies on unitarity. So it violates unitarity as far as we can tell. And I'll show you exactly why that happens. Okay. And then the name of the game is going to be what is the minimal addition that you can make to modify the spectrum to restore unitarity. Good. Okay, so the strategy.
Can I just ask?
Yep,
yeah.
Please.
It's, I mean, dangerously close to the sort of Gödel universe, ADS asymptotic.
Well, Gödel universe has closed time-like curves. I should say, maybe when I say ADS here, I mean the universal cover of anti de Sitter space.
Okay.
Is that what you're?
No, I mean, if you are allowing matter in there, I think Gödel universe needs sort of dust. So you have swirling dust and ADS.
The matter that we're adding is not dust.
No.
I haven't told you what matter I'm adding yet. You're not allowed to complain about the matter I add until I tell you what it is.
Okay, very good.
Yeah, okay, good. Fair enough? Okay,
yep.
Great. Indeed, maybe I can anticipate your objection, which is that the matter that I'm going to add is not perturbative, right? So it is not going to be a quantum field in an ADS background. If I did so, then there would be very small perturbative fluctuations. They could collapse, they could form singularities, all kinds of weird stuff could happen. What I'm going to discover is that there is a unitarity argument that tells me that the spectrum I described above doesn't work, but that there is a minimal addition to the spectrum that does work, but it does not involve the existence of perturbative states. They're non-perturbative in a precise sense that I will describe if I have time. But I don't want to okay, but please ask more questions if anyone has questions. Okay. So what is my strategy going to be? My strategy is that I'm going to construct the partition function of this pure theory of gravity. What I mean by pure gravity is the theory described up above, where we have no degrees of freedom aside from the metric. So I'll try and, to the best of our understanding, using our best understanding of what we mean by quantum gravity, to construct the exact quantum mechanical partition function of this theory of pure gravity. I'll show that the spectrum that you get out violates unitarity in a very precise way. And I'll discover that there is a minimal set of additions that cure this. And that then and that these have a physical, that is to say, a geometric interpretation in terms of orbifolds. Okay. So in particular, just to sort of give you the answer now in case I don't get to discuss it in much detail later. When I talked about the spectrum of the theory that I described up here, I was talking about the spectrum of the theory in terms of smooth solutions of general relativity in an appropriate sense that we'll describe. And the proposed modification that restores unitarity, that cures this violation of unitarity that we're going to discover, is very simple. It is just to replace the word smooth manifold by the word orbifold. And we'll see exactly what that means and where that comes from if we have time. Okay. So let's try and implement this strategy in more detail. So what I'm going to try and do is construct a partition function which, in the language of conformal field theory, we would call the torus partition function. Or in the language of conventional physics, we would just call the finite temperature partition function. So here, L0 and L0 bar are, I guess I called it E, just the left and right moving combinations of energy and angular momentum. In the conformal theory interpretation, you think of them as the two generators of the left and right moving Virasoro algebra. And the way that we would try and construct this in a gravitational theory is by doing a path integral. So in particular, the way that we construct a thermal partition function of the theory is by performing a Wick rotation from Lorentzian to Euclidean signature, and then periodically identifying in Euclidean time. Right? That's how we study finite temperature physics. And we can do the same thing in the theory of gravity. So in particular, that means that the boundary of my theory, so previously my boundary was a cylinder where T was a Lorentzian time direction, but I now replace that with a Euclidean time direction. So I'm studying a Euclidean theory of gravity, and I periodically identify. And I periodically identify with some period that in the thermodynamic language you would call an inverse temperature. And in the CFT language, you would call this the modular parameter of a torus that lives at the boundary. So indeed, what this means is that the cylinder at the boundary has now become a torus. And when I compute this path integral, I want to sum over all three-dimensional geometries whose boundary is a torus. And tau and tau bar appear here. So tau is the modular parameter of that boundary torus. Its imaginary part is the inverse temperature. And its real part is an angular potential, okay, which in the language of this geometry that we're drawing here, the way that I would introduce an angular potential is I would glue the top and the bottom of this torus together, of this cylinder to form a torus, but I would glue them together with a twist by an amount that would be this angular potential. Okay. So how would I go about trying to do this computation? So I'm trying to do a computation where I sum over all Euclidean three manifolds whose torus is a boundary. Okay, so in a higher dimensional theory of general relativity, this would be an impossible task. But remarkably, there's a sense in which you can do this computation exactly in 2+1 dimensions. Good. So Robert asks the question, why am I working at finite temperature? I've chosen to work at finite temperature because that gives me a nice way of studying the spectrum of the theory. Sorry, can you guys still see my tablet?
No, we lost it.
My tablet disappeared. Huh. Okay, let's see what's going on here. Is my tablet back? Okay, good. I think I must have pressed a button accidentally there. Great.
Right.
Okay, so Robert's question is, why am I at finite temperature? I am choosing to study the theory at finite temperature because the partition function of a theory at finite temperature is the thing that encodes the spectrum of the theory. And I'm interested in studying the spectrum. There are other things that we could compute, but this is the thing that I know how to compute. Good. So how am I going to try and compute it? Well, the way that I'm going to try and compute it is as follows. So this partition function. So let's first imagine how I would compute this if I were just working in a classical theory, in the classical limit. In the classical limit, the way that I would compute this theory, sorry, is, can you guys see what I'm somehow, okay, there we go. Sorry, it just seems to be updating a little slowly. So in a classical theory, the way that I would compute this is by summing over all classical solutions to the equations of motion. So in particular, I would sum over all solutions to the equations of motion. What are these solutions? These solutions are locally Euclidean ADS geometries whose boundary is a torus. Euclidean anti-de Sitter space is hyperbolic 3 space. And the geometries that we're talking about are quotients of hyperbolic 3 space. And you can actually prove that the only quotient of hyperbolic 3 space whose boundary is a torus is a quotient by Z. So those are the classical solutions. And classically, you would compute this partition function by summing the classical solution over all of these geometries. Good. So John's question, is finite T equivalent to replacing the cylinder by a torus? Yeah, the answer is yes. The cylinder was the boundary in Lorentzian signature. When we go to finite temperature, we take T to IT and periodically identify, which replaces that cylinder by a torus, which is what I have drawn here, where the top and the bottom of the cylinder are identified. Okay. So hyperbolic 3 space is just the Euclidean geometry that you get when you take anti-de Sitter space and take T to IT. It's the prototypical, it's the prototypical maximally symmetric geometry in 3 Euclidean dimensions with constant negative curvature. Good. So the question, there's also a question, is the Wick rotation trivial for rotating backgrounds? No, it's very much not trivial. Okay. I don't want to get too far into the weeds here, but when you turn on this angular potential, so in fact, there are solutions that you can, in a sense, interpret as Euclidean continuations of rotating solutions. That Euclidean continuation is a little subtle. If you really wanted to take it seriously, you would have to take the angular momentum to I times the angular momentum. I'll just say that it's a little subtle and I don't want to get into it in too much more detail. Good. Okay. So classically, the way that we would compute this is by finding all 3 manifolds with a torus boundary and summing over them weighted by the action. Now, of course, when I say weighted by the action, I mean for the classical piece, the action divided by h bar. But I've been using, I've so far set h bar equal to, I've so far set h bar equal to 1, but it turns out that h bar is also 1 over the central charge. So that in that expression for the central charge, this goes like 1 over h bar. Good. Yes, okay, I think I've answered all the questions. Good. Okay, there's another question. The fact that not taking the universal cover in ADS also covers the torus of the boundary related to, okay. ADS is a Lorentzian geometry. I'm working here in Euclidean signature. So all I am doing is I am classifying the quotients of hyperbolic 3 space whose boundary is a torus. Turns out that one can do that classification, and that right. And it turns out they're classified by SL2Z, although I don't necessarily want to get into too much detail there.
Okay, I'll just say a word because I maybe didn't express it correctly. If you didn't take the universal cover ADS, the boundary would still be a torus, not a cylinder. Is there any connection between that and the finite temperature?
It would be a Lorentzian torus. So if you don't take the universal cover of ADS, you get a space-time with closed time-like curves. I don't know how to define a good theory of physics in a space-time with closed time-like curves. So I think that might get us a little far afield. We could have a more detailed, okay. Maybe I can just end the, okay. I think that might be all I want to say about that. Although, you could distract me and I could go on for a very long time about the contour of integration over the space of metrics that we're discussing here. But for the time being, so in order for me to write down this partition function, I need to make an assumption for exactly what it is I mean by the integral over the space of metrics. Here, I'm working in Euclidean signature to compute a finite temperature partition function. So what I mean by an integral over a space of Euclidean metrics is that I mean an integral over the space of real Euclidean metrics. Something like the non-universal cover of anti-de Sitter space is a Lorentzian geometry that we usually wouldn't consider as contributing to a Euclidean solution, to a Euclidean path integral. There are some circumstances, more subtle things that can happen, but let's not worry about that for now. Good.
Okay, just to be a pest one more time. Going to the Euclidean signature, doesn't that mean replacing anti-de Sitter by de Sitter?
No. So going to Euclidean signature means performing a complex change of coordinates that takes t to it. And when I do so, that changes the geometry from a Lorentzian geometry to a Euclidean geometry. It does not change the cosmological constant, which is what would take anti-de Sitter space to de Sitter space, right?
Okay.
Anti-de Sitter space is the Lorentzian version of hyperbolic space in the same way that de Sitter space is the Lorentzian version of a sphere. Good. All good questions? Yeah, right. There was a question about what is hyperbolic 3 space. I think I addressed that. Great, thank you. Okay, now, it turns out that it is completely possible to find all of the quotients of hyperbolic 3 space whose boundary is a torus. They're all quotients of hyperbolic 3 space by some subgroup isomorphic to Z. That is a subgroup of the SL2C isometry group of hyperbolic space. And it turns out that they are classified completely by cosets of SL2Z. So in particular by the cosets of SL2Z mod Z. How do you think about that? Well, I told you that my boundary is a torus. And the Euclidean geometries I'm summing over are all of the solid donuts that fill in a boundary torus. Okay? So for example, here I've drawn a boundary torus, and I've drawn one solid donut that fills it in. So in particular, the circle that I have drawn here is contractible in the interior. But there are an infinite number of other ways of filling in the boundary torus with a solid donut. And they correspond to all of the different possible cycles in the boundary torus that can be chosen to be contractible in the bulk. So for example, there's another solid donut, which is given not by the inside of the torus I've drawn here, but by the outside of the torus. And that's a solid donut where this cycle is contractible. Now, what is the physical interpretation of that geometry? Well, the cycle that I have drawn here is Euclidean time. And Euclidean time being contractible means that there's a place inside the geometry where the coefficient of dt squared goes to 0. What does that mean in Lorentzian signature? A place where the coefficient of dt squared goes to 0 is an event horizon. So the Euclidean geometry where I fill in the boundary torus in such a way that this cycle is contractible, what is that? That is the Euclidean continuation of a black hole. Okay. So in this sum over SL2Z that we are describing here, you can think about this as a sum over all Euclidean continuations of black holes. Now, so far I'm just talking about the classical piece of the sum. But for every classical solution, I could imagine working harder and finding a one-loop correction. And then working even harder and finding a two-loop correction. And then working even harder and finding a three-loop correction, and so on and so forth. Now, if it were possible to find the infinite series of subleading corrections around each of these saddle points and sum them up over all possible saddle points, then this would be an exact answer for what we mean by the path integral of three-dimensional geometry, or the path integral of three-dimensional gravity. In particular, the statement that I am making, and it is a bit of an assumption, is that if you have a quantum theory where you can not only find all of the classical solutions, but find the infinite set of perturbative corrections around each classical solution, then this would be an exact answer for the path integral. In a typical complicated quantum theory, this would be an impossible task. But it turns out that in the theory that we're studying, this can actually be done. I won't go into any details of how it's done, but it turns out that it's possible to not only find the infinite set of subleading corrections, but also combine them together with the infinite set of saddle points to sum over to get something that you could plausibly call the exact path integral of three-dimensional general relativity. And this is now a fully quantum mechanical answer. So I won't really tell you in any detail how this is done. So when you do it, you get an answer for a partition function that is known as the MWK partition function. And I won't write it down for you because the expression for it is rather complicated. I'll just tell you what the corresponding spectrum looks like. So in particular, if you think about this as a trace of Q to the L0, Q bar to the L0 bar, where Q is the usual variable associated to the modular parameter tau, and L0 and L0 bar are energy plus or minus angular momentum. You can extract from this the spectrum of the theory. And what does the spectrum look like? So now I'm going to draw a very similar picture to the one I drew in the beginning of my talk. So I'm going to characterize the spectrum in terms of its energy and angular momentum. But now this is an exact quantum mechanical calculation of the spectrum as done by a path integral. And what does it look like? Oh, good. There was a question about Dustrumat-Heckman. Okay, it is related to Dustrumat-Heckman, I believe. But okay. Yes, I believe it is related to Dustrumat-Heckman. Although when we did the computation, we did it in a much more lowbrow language. But I think almost surely you could rephrase it in the language of Dustrumat-Heckman as a sort of localization calculation. Great.
So it's an example where the Gaussian approximation to the saddle point is exact.
Yes, absolutely. Absolutely. Good. I don't want to get too distracted by that statement because I have already gone on for most of my hour, but yes, It's an example where the Gaussian approximation is exact. But what does the result look like? So here, what I'm going to do is, to make my life simple, I'm not going to worry about the boundary gravitons, okay? So what the spectrum looks like is it looks almost exactly like the spectrum of the classical theory that we described earlier. So it has a set of states that look like black holes, but it has a few problems. So the first is that the spectrum is continuous. Now, for a classical theory, to have a classical spectrum that's continuous is not a problem. However, remember that gravity in ADS is like gravity in a box. And whenever you study physics in a box, if you work at finite h bar rather than in the classical limit, you should have a quantized spectrum, not a discrete spectrum. So it's a problem for our interpretation of this as a quantum mechanical theory if you have a continuous spectrum. There are ways that one might hope to get around this that I unfortunately don't think I have time to comment on. But what I think is a more serious issue than the fact that the spectrum is continuous is that the density of states that you get becomes negative near the boundary let's call it the cosmic censorship bound. So this set of 45-degree lines is what we would call the cosmic censorship bound, because it's where the area of the event horizon of the putative black hole shrinks to 0 size. And it turns out that if you zoom in on what the spectrum looks like in this region, it turns out that it's negative. Okay. So having a density of states that is continuous, I could live with, but in a unitary theory, having a negative number of states is not something that I can live with. Okay. This violates unitarity. Okay. Good. There's a question of how general the Brown-Hanot boundary conditions are. Good. So there are slight generalizations of the Brown-Hanot boundary conditions. As far as we know, the Brown-Hanot boundary conditions are the correct ones to give you a theory which has a CFT dual. People have investigated other more relaxed versions of the theory where you have more general boundary conditions. Unfortunately, I don't have too much to say about this right now. Good. How do I extract the density of states? Well, I have a partition function here, which is the integral of the density of states times q to the L0, q bar to the L0 bar. I extract the density of states by doing an inverse Laplace transform. Good. Okay. So
But the partition function is positive, right?
yes.
The
The partition function is positive, but the density of states that you extract from it is not.
So could it overpower? Could it, I mean, you have presumably some positive density of state part and then some negative, right? So
Yes, so the partition function is positive. But one thing that I believe about quantum mechanics is that the number of states of a given energy should be a positive number. And having a number of states at a different energy that's positive is fine, but won't help me if the number of states at some other energy is negative, right? When I say that this is a violation of unitarity, I literally mean that when I quantize general relativity in 2+1 dimensions, to the best of the way that I know how to quantize it, I find that the number of states with a particular energy and spin is negative. So there's a good question, could you allow punctures or extra handles on the torus? In the sum over geometries, it turns out one can classify all of the geometries that have a torus boundary and are classical solutions of the equations of motion. And in that case, extra handles on the torus, extra handles in the interior of the spacetime are not allowed. You could certainly consider the boundary being not a torus, but a higher genus surface. And there's a very analogous story, but it actually turns out to be a much richer story. I could talk about that if you wanted to, but let's not get into it now. As far as allowing punctures, let me return to that in a minute. Good. Great, good questions, all of them. Okay, in the interest of time, let me just tell you what the answer is. It turns out that this negativity can be cured if we add new states to the theory. And in particular, if you add a state, so the first and strongest negativity in this density of states can be cured if we add a state with dimension c over 16. Okay? So I remind you that the size of the gap here, so let me actually draw a picture over here. So here, I'll just draw the vertical axis. So this is the energy axis. So the ground state has energy 0. The lightest black hole has energy c over 12. And it turns out that if you want to cure the negativity, one strategy to do so would be to say, well, it turns out you can cure the negativity by adding new states in the theory. And so you could say, how heavy can you make the first state that you add in the theory in a way that cures this negativity? And it turns out that the first state you need to add is a state with energy c over 16, which lives right here. And then, however, it turns out that that doesn't quite do it for you. You still need to add another state with energy c times 2 over 27, which lives somewhere here. And then you proceed with the argument, you find that you need to add another state with energy c times 5 over 64. And then another state with c times 2 over 25. And so on and so forth. Okay. And you end up needing to add a bunch of states here in this window. And I've drawn for you, I've written down for you just the first few terms here. But if you stared at it for a few minutes, you could find the pattern. The pattern is that it's c over 12 times 1 minus 1 over n squared, where n is an integer. So the conjecture then is that we must add these states in order to have a consistent theory of gravity. And in particular, a theory of gravity whose spectrum is unitary. And it appears that one needs to add an infinite number of them. Notice that these are all lighter than the lightest black hole in the theory, which had energy c/12. So the question then is, what is the geometric interpretation of these states? And I could go through an argument which makes which makes this much more clear. But in the interest of time, I'll just tell you what the answer is, okay? Which is that these are orbifolds of ADS by Zn. So in particular, if you just look at the constant time slice of ADS, so this is sort of a top-down view of the constant time slice of ADS, which is the hyperbolic disk, then what you can do is you could quotient by a rotation by an angle 2 pi over n. And when you do that, you're going to get a conical defect at the origin with a conical defect angle of 2 pi over n. Okay, so we're quotienting here by e to the 2 pi I, 1 over n times the rotation generator, d by d phi. Okay. Good. John says the formula doesn't agree. Okay, the c/12, it's possible that I copied down these numbers wrong. Okay, I think it's okay. Anyway, the formula is c/12 times 1 minus 1 over n squared. Always possible I made a typo in writing this down. There's a 16, there's a 2 over 27, there's a 5 over 64. I think it's okay. Good. Okay. So conjecture. Is that at least in this relatively simple theory of gravity, we should replace the notion of general relativity as a theory of dynamical geometries, which are smooth manifolds, to a theory of orbifolds. There's an interesting question whether there are any relation to Virasoro null states. Not as far as I understand. There's an interesting interpretation of Virasoro null states as conical excesses, whereas what I'm talking about are conical defects. So I thought about that, but I don't see any relationship. Let me make one final sort of set of observations, which you might think of as additional evidence for this. So one observation is that you can actually compute the quantum corrections around these orbifold geometries. You can include them in the sum over geometries, and you actually get a surprisingly interesting answer. Okay? So in particular, the first objection that anyone would make to a proposal like the one that I have written down above is that I am adding an infinite number of states to my theory, right? Because I'm adding states with energy c/12 times 1 minus 1 over n squared for any integer value of n. Now, adding an infinite number of states whose energy is bounded above seems like a problem. Right? For example, it seems like the partition function of the theory would diverge. Right? The partition function of the theory is the sum over all of the states weighted by e to the minus beta e, where beta is the inverse temperature. So if you add an infinite number of states with a finite energy, that's going to diverge. It turns out, however, that that doesn't happen for a rather remarkable reason. Okay? The remarkable reason it doesn't happen is because I lied to you earlier. Okay? Because it turns out that there was one other problem with the pure gravity partition function I wrote down above. Okay. The problem is that in addition to the density of states being continuous, there is also a negative delta function that appears here. So there's a negative delta function located at exactly E is equal to C over 12. So in particular, if you study this quantum theory of gravity as a theory of smooth manifolds, it looks like you have exactly -1 state precisely at energy C over 12. Where does that come from? That -1 comes from the infinite sum over SL2Z here. In the language of physics, what we're doing is we're doing a sum over instantons. We're summing over an infinite family of instantons and seeing that they resum to give you exactly -1 state right here at threshold. Now, if I redid this, but adding in also my conical defects, if I add in a Z2 conical defect, it'll turn out that you get -2 states right at threshold. If you add in the Z3 conical defect, you get -3 states at threshold, and so on and so forth. And so at the end of the day, it turns out that what happens is that although I am adding a positive infinity number of states with energy slightly below C over 12, I also, coming from the infinite sum over instantons, get a negative infinity number of states right at C over 12 in such a way that everything actually converges. And so what you find is that the infinite number of states that you're adding cancels a minus infinity from the sum over instantons. That is to say, the sum over geometries. There's a question about how these things cancel, and indeed it happens exactly through some zeta function regularization. So when I said, for example, that I had a minus delta function here, one objection you could have made was the following, which is that I computed this partition function by summing the actions of a bunch of manifolds. That should be a sum of real numbers. How can a sum of real numbers give me a negative answer? And the answer is that the sum actually diverges, and I need to regulate it somehow. There's a complicated story of how this regulator works. The answer, as far as we can tell, is completely unambiguous. And the result is that essentially you get a zeta function regularized answer, and you end up with a -1 there. Okay. And so indeed, that -1 comes from a zeta function regularization. Okay. The fact that one has to regularize a sum of this sort is not maybe so surprising from the point of view of quantum field theory. Good. There's a question, if we sum these energies, do you get infinity? Yeah, so maybe this is addressing the point earlier. So there is one plus infinity that gets canceled with a minus infinity in such a way that you get a finite answer. This is a kind of remarkable situation where you have an infinite number of possible saddle points that are contributing to a path integral. And they are conspiring in such a way as to give us a finite answer. I take this as at least some indication that we might be on the right track here. Let me end with one. Okay, there is a question. If you sum these energies, do you get infinity? Can you sum the massive states to form BTC black holes? That's a sort of interesting question. When I said that these states are non-perturbative, one thing that one means by that is that they have energies of order the central charge, okay? That is to say, energies of order 1 over h bar. Usually in a quantum mechanical theory, if something has energies of order 1 over h bar, it's some kind of non-perturbative effect. And it turns out that these conical defects, so you can prove a theorem in two-dimensional conformal field theory, which is that if you have two very light states with energy much less than the central charge, they can always form bound states. It's a consequence of crossing symmetry and unitarity. It turns out that the minimum energy a state must have in order to not be able to form two particle bound states is that its energy must be bigger than C over 16. It turns out that these are precisely, so these energies are precisely those that have the property that they can't form bound states. Now, the question though was whether you can sum these massive states to form a BTC black hole. If you ask me secretly what I would like to do in order to relate this to black hole physics is, although I have been discussing this theory as a sum over geometries in Euclidean signature, we're talking about a Lorentzian theory. And I think the best way to proceed when you want to understand a Lorentzian theory is to study the Lorentzian theory. And so if you ask me the relationship with black hole entropy, I would say that black hole entropy should be found by thinking of general relativity in 2+1 dimensions as a theory on the dynamics of moduli space. In particular, it turns out that you can solve the constraint equations of general relativity in 2+1 dimensions. In the physics language, we would call these constraint equations the Hamiltonian and momentum constraints. In the mathematics language, we would call them the Gauss-Codazzi equations. You can solve these things in 2+1 dimensional general relativity. And you find that 2+1 general relativity is a theory whose phase space is the cotangent bundle of moduli space. And here I mean the moduli space of Riemann surfaces. So I think that a better way of thinking about quantum gravity in 2+1 dimensions is a theory of quantum mechanics on moduli space. And the way that I would like to reproduce black hole entropy is by quantizing moduli space. And here I mean literally quantizing the moduli space of Riemann surfaces. And the role of orbifolds then would be that I should quantize the moduli space, not just of smooth Riemann surfaces, but of cone surfaces where you allow these orbifolds. I have things I could say in that direction, but nothing I think that is completely satisfactory. If, for example, I could reproduce the Bekenstein-Hawking formula for black hole entropy, I would be giving that talk instead of this one. Maybe I'll mention one other final comment, which is that the spectrum that we get is now positive, but it is still continuous. And over the last, I would say, year or two, this is a subject that has acquired, a lot of discussion in the literature. And one proposed resolution of this puzzle is that possibly three-dimensional gravity, or possibly any theory of gravity, is not describing a particular quantum mechanical system, but an average over many quantum mechanical systems. So possibly three-dimensional gravity or higher dimensional gravity is not a quantum mechanical system, but an average of many quantum mechanical systems. An individual Hamiltonian has a discrete spectrum, right? If you take, an n by n Hermitian matrix, then that has a discrete set of eigenvalues. But if you average over the space of all n by n Hermitian matrices, you get a continuous density, eigenvalue density. For the Gaussian ensemble of Hermitian n by n matrices, you get the famous semicircle law. But for other ensembles of matrices, you get other kinds of distributions. And so I think one very interesting suggestion is that the continuous density of states is not something that we should try and cure within our theory of gravity. Instead, we should interpret it as coming from an average over many quantum mechanical systems. So there is a question, can you give a string interpretation to this idea? No, not, well, not, I don't have anything to say about that. Well, I have some things to say that I'm not going to say. But I will say that there was a very beautiful paper published last year where there was an even simpler theory of gravity in 1+1 dimensions, which is a theory of constantly negative curved Riemann surfaces. In that case, the spectrum is continuous, but it turns out to have a beautiful interpretation. And in particular, it turns out to come from an average over an ensemble of random Hamiltonians. But it is an ensemble of random Hamiltonians with a very particular probability density. So not a Gaussian probability density, but instead the density that is associated with the Mirzakhani recursion relations in topological recursion. So yeah, this is JT gravity that I'm referring to, Robert. Okay, there's a question. I'll get back to that in a second. Right. So there was a beautiful result last year, which shows that there is a two-dimensional theory of gravity. Basically, so it's a theory of constant negatively curved surfaces, which means that the path integral is an integral over a space of constant negatively curved surfaces. That is to say, is an integral over the moduli space of Riemann surfaces. And it turns out that integrals over the moduli spaces of Riemann surfaces can be reorganized into n integrals over spaces of n by n random matrices in a large n limit. And and there's a beautiful story, I guess, due primarily to Eynard and Orantin, relating these integrals over moduli spaces of Riemann surfaces to n by n random matrix integrals. And if you ask me what I believe about three-dimensional gravity, is that I believe something very similar is true. Namely, that the fact that the spectrum is continuous is not a problem to be solved, but rather is a reflection of the fact that it's given by some disordered theory where one averages over many quantum systems. I have some words to say about that. The reason why I was late giving my title for the talk is that I'm writing another paper where some of these things can be made precise, albeit in a slightly different model. In particular, one can write down a theory of gravity that is equivalent to not a particular conformal field theory, but an average of many conformal field theories. And one can go through this entire discussion in quite detail. I decided not to talk about that because I think that it's not fully baked yet. But maybe if I give this talk again at some other point, that's what I'll talk about. There's a question, is there an assumption that this average is continuous? Couldn't it be a discrete average? So one could also talk about a discrete average. It's hard to get a continuous density of states from a discrete average, however. Yeah, I don't have much more to say about that.
Alex, we're getting late.
I apologize for going over time. Sorry about that.
No problem. The crowd is still all there. But before asking for more questions, I suggest that we turn on our microphones and we thank the speaker.
All right,
so,
thank you.
Thank you very much, Alex.
Thank you.
Very good. And so if you want to leave, please leave. But of course, we can ask the question, and I maybe would prefer now to raise your hand so we have an order of people asking questions. Actually, there's a last question in the chat room, Alex, that you want to address.
Good. Oh, I see. What happens if instead of adding states, you consider different classical theories, such as, I don't even know, Milk-Baker gravity, including a torsion degree of freedom? Yeah, there's a sense in which this theory where you turn on a gravitational Chern-Simons term is one where there's a torsion degree of freedom. I'm not familiar with this theory of gravity that you're referring to, the Milk-Bakler theory, but there may be good things to do there. I don't have too much to say about the theories with torsion. I mean, when you turn on this gravitational Chern-Simons term, many of the things that I have said go through, but not all of them. Yeah. There's other questions?
I'm surprised that there's no hands raised, so I'll go for one. The partition function that you wrote before the addition of the orbifold terms, was it modular invariant?
Yes. Yeah.
And of course, the one that you've added the orbifolds still is.
Absolutely. Yeah. So I skipped a bunch of steps here, but yes, the effect of this sum over SL2Z is to restore modular invariance.
Okay.
And when I say add orbifolds, what I really mean is when I compute the partition function of the theory, I continue to do an analogous sum over SL2Z to maintain modular invariance, right? You know, the reason why I didn't write down the spectrum explicitly and only wrote down this cartoon is that when you do that sum over SL2Z, you can do it, but you're not gonna like looking at the answer because it's complicated. But yeah, absolutely modular invariant.
And the sum over orbifolds by itself, does it represent any conformal field theory that we should know about without the rest of the, with only the orbifolds by themselves?
It might be related to Liouville theory. I mean, you know, I don't have anything. It might be some analytic continuation of Liouville theory. Like in Liouville theory, you have vertex operators of the form e to the alpha phi, where phi is your Liouville field. And then if you want something that is like you could sort of imagine that single valuedness, you know, if you took alpha to be imaginary and phi to be periodic, there's some quantization condition on alpha, which is related to the energy of the state. I'm pretty sure that gives you the exact same quantization condition on the energies that I wrote down. So there may be a sense in which you should interpret these orbifolds in Liouville theory. You know, there was a very nice set of papers by Krasnov. Maybe there's a Z instead of an S, I'm not sure. There's a very nice set of papers by Krasnov in the early 2000s where he, you know, where he discussed Liouville theory and its relation to 3D gravity and black holes. And I suspect that you might be able to find an interpretation there. Good, so there's a question for references on the 2D result, on the continuous spectrum arising. Okay.
And you have a question by Fabio, who has raised his hands.
Oh, good. Is there an assumption? Wait, okay.
Go ahead, Fabio.
Oh, Fabio. Yeah. Fabio in person, not Fabio on the chat. Oh, Fabio, why don't you ask your question?
Yeah, okay. Alex, thank you very much for the nice talk.
Thank you.
And I'm just to say I'm talking from Chile. You're at Centro de Estudios Científicos.
Oh, good. Say hi to all my friends there. I'm not sure which ones.
Okay.
Yeah.
So if you may, I have two questions. So you mentioned about Liouville theory, but there is this problem that in the central charge would be 1 in principle, like in the semi-classical limit. So how can you?
Well, you could consider Liouville with any value of the central charge.
Right, but when you try to calculate the the Cardi formula.
I see. No, sorry. That's C equals So okay, right. I don't think one wants to take Liouville theory too seriously as a theory of gravity. It doesn't have enough states to explain black hole entropy. I mean, as you were just referred to, because the number of states, the way that I would say it is that the number of states in the vacuum module of a CFT grows like a CFT with Cardi formula central charge 1 instead of a large central charge. So I don't think you have much hope of getting black hole entropy, that is to say Cardi's formula, out of Liouville theory. But the question was more about the interpretation of these orbifolds. And I think you might be able to interpret those in terms of Liouville theory. Great. So there was a question asking for references on the 2D result. Yeah, so I assume you mean this JT gravity as being related to an integral, as being related to this topological recursion. So that was a lovely paper by Saad, Schenker, and Stanford. Came out a year ago. I think that this paper is quite beautiful. You know, it provides a very physical interpretation of the topological recursion machinery of Eynard et al. And they have some very beautiful results that go beyond things in the mathematics literature. So for example, one of the things that they do is they use instanton methods to study large genus asymptotics of moduli spaces of Riemann surfaces and go beyond, I think, some of the results in the math literature. Yeah. Any other questions?
Manu?
Yeah, I have a question.
Manu?
Your black holes are surely local states, localized states. But you don't, I mean,
well,
the question would be, could you have two
yeah,
of them in space-time?
the answer is no, you can't. So this is 2+1 gravity is very different from higher dimensional gravity. So it usually, you know, I told you that gravity in ADS is like a box of size L. And you might think that you could make a black hole whose size is much less than the size of the box, and that very far from the black hole, it just looks like anti-de Sitter space again, and so you could put two of them, right? And there would be no problem. Turns out that's not how general relativity in 2+1 works. The force of gravity doesn't fall off quickly enough at large distances in order for that to work. All of the black holes that we're talking about, they have areas that are of order the ADS scale, right? So one way of understanding the energy being of order the central charge, another way of writing that is that the area of the black hole is of order the ADS scale. So all of these black holes, you know, if this is ADS, every black hole takes up an order 1 fraction of the ADS volume. It turns out you can't write down solutions where you have two black holes sitting next to one another. If you look in the literature, there are things that are called multi-black hole solutions, but that is not what is meant. That is not what is meant, but they're not two black holes sitting in the same asymptotic region. When people talk about the multi-black hole solutions, they talk about things with multiple asymptotic regions. In the same way that the Schwarzschild black hole has two asymptotic regions. You can, yeah.
Okay.
Great.
Well, if there's no more questions, again, thank you very much, Alex.
Thank
and
you all.
we'll cut the seminar here. Thank you very much. Again,
Great.
I don't know if you want to open your microphones to say thank you, but here, thank you very much.
All right. Thank you, everyone.